I now have the great pleasure to introduce our first speaker, Marcus du Sautoy. Marcus du Sautoy is the Charles Simonyi Professor for the Public Understanding of Science, and he's also Professor of Mathematics at the University of Oxford and a Fellow of New College. He's the author of 3 books, The Music of the Primes, Finding Moonshine, and most recently, The Number Mysteries. He has presented numerous radio and TV series, including a 4-part landmark TV series for the BBC called The Story of Math. In 2009, he was awarded the Royal Society's Faraday Prize, the UK's premier award for excellence in communicating science. So if Gilbert and George say art for all, we could say Marcus du Sautoy is science for all. He received an OBE for services to science in the 2010 New Year's Honours List. Marcus will present today his mathematical maps, and it's not the first time that we collaborate with him on a Serpentine project. Marcus du Sautoy did an extraordinary text and presentation at the moment of our Gerhard Richter show, which had a lot to do with numbers and painting. And he also, more recently, did an extraordinary text on our Anish Kapoor project, which you can see whenever you have time in the next 6 months in Kensington Garden. And Anish Kapoor also for this project actually made a map, so you can pick up the map of Anish Kapoor and at any time go on a walk. But now Marcus du Sautoy and his mathematical maps. A very warm welcome to Marcus.
Well, I'm very impressed to see so many people out for double maths on a Sunday morning, so thank you very much. What is this a map of? The London Underground. But it's not the usual map that we use for the London Underground, because knowing the geometric map of the London Underground isn't very helpful. What you want to know is how the stations are connected together. So in fact, what we do is to morph the map to make it look much more approachable and accessible, so you can actually navigate the London Underground. It's not important that the distance between the 2 stations is not represented here. You want to know how the thing is connected together. And this is a new way of mapping that was introduced by mathematicians in the 20th century. It's an area called topology. Geometry is geometric measuring the Earth. Topology is about this bendy sort of geometry where you can mold things until you see a much more acceptable and helpful map. Actually, topology started with a little afternoon puzzle that the residents of Königsberg used to do in the 17th century. Königsberg in Prussia at the time has the River Pregel. There's 2 strands of the River Pregel that meet, and then there's an island in the middle of the Königsberg, and then the river runs out to the Baltic Sea. And there are 7 bridges which connect this island and city together. And the challenge for the residents of Königsberg was to see whether they could cross all of the 7 bridges once and once only and return to where they came from. But as hard as they tried, they just couldn't find some way to do it. Where every Sunday afternoon they go out, try and find their way around all these bridges, these 7 bridges, and they would always find there was one bridge that was left over. And it was Leonhard Euler who heard about this problem when he moved from Switzerland to Leningrad, St. Petersburg, and he realized that actually it's not important the actual geometry of Königsberg. What's important is how these maps, how these bridges connect the different parts of the island together and the rest of the city. So he realized this is a much better map of Königsberg to try and answer this problem. So the challenge suddenly becomes not one about going over all of these bridges, exhausting yourself on a Sunday afternoon, but whether you can draw this diagram without taking your pen off the paper and complete the whole diagram. So I'd like to offer a challenge to anybody. Does anybody want to have a go at trying to draw this picture without taking their pen off the whiteboard here? So I need a volunteer, please. Have a go at doing the bridges of Königsberg. Not much exercise required, just a bit of arm work. Anyone like to have a go? Oh, there we go, good. I know it's Sunday morning and double maths on a Sunday is... So have a go. Of course, this thing is set up so that she will not be able to succeed, but don't worry. But maybe he thinks, we haven't tried some particular way. So he's done the figure of 8, and now he's come around to D, and now you've got 2 bridges to cross, one going to B and one going to C, and you find that you can't do it. Exactly. So it's rather an unfair challenge. But here's another challenge. Do you want to have a go at this one? So this one seems impossible. What about this one? Do you think you could draw that one? The little kind of envelope shape. Okay, so very good. Excellent, you did that one. So now you've had a sense of achievement. Give him a round of applause for drawing this one without taking your pen off the paper. Now what Euler realized was you need to understand how these points are connected together. And actually, if you're making a journey, every point that you visit on your journey has one bridge coming in and then another bridge coming out. So all the points in the middle of your journey are actually going to have an even number of bridges, one coming in and a second one coming out. And if you revisit that, you come in on another bridge, you have to go out on another bridge. So there are always an even number of bridges, except for the place you begin and end where they're allowed to be an odd number. Well, if you look at this, the bridges of Königsberg, the topological map of the bridges of Königsberg, every point in the map has an odd number of bridges coming out of it, so it's impossible to navigate this map. Whilst the envelope here has two places, my volunteer very cleverly started at the bottom, which are the two places with an odd number of bridges coming out. That's where you begin and end your diagram. And this is an area of mathematics called topology, which sometimes is called bendy geometry, where it's not the actual geometry of the thing, but you can mold these things. So you've been eating bagels maybe at brunch this morning and also holding a coffee cup. For a topologist, these two things have the same map. They are the same shape because you can mold one into the other. Now, these maps are very useful for navigating London, but they're more useful for navigating something much bigger. If you want to create a map of the universe, then topology and the mathematics of topology rather than geometry, there's no way you're going to do it, topology is much better. So I'm going to use some of this mathematics to show you how to map the universe. We're going to start with a very small universe, actually. This is a universe some of you may have played in the game of asteroids. I hear some chuckles, a sort of old 70s kind of game. This asteroids is a finite universe. It's all contained inside the computer screen here. It's a two-dimensional flat universe. There's something special about this universe because it doesn't have any walls or boundaries. Because when you go out the top of this universe, you reappear at the bottom. And when you go off to the side, you will reappear on the other side. So actually the universe feels like it's not got any boundaries. I mean, this isn't the Truman Show where suddenly you hit a wall when you get to the edge of it. But it is a finite universe. Now, what is the shape of this universe? Well, topology allows us to actually see what this shape is, because we can mold this screen and actually construct the shape of the universe that this spaceman in this two-dimensional game of asteroids is floating around in. Because the top and the bottom of the screens are joined together. If you go out the top, you come in the bottom. So you join those and you make a cylinder. And now the other two sides of the screens are joined up, so when you join those two up in the connection, you get the shape of a donut. Or a torus, as we call it in the mathematical trade. So topologically, this map of asteroids, this little finite dimensional universe, is actually, you can wrap it up in 3 dimensions, bend the shape, and you get this shape of the donut. Okay, but we live in a 3-dimensional universe, so what is the possible shape of the universe that we live in? Well, I think most people have a sense that, well, does it have a shape? Can you really map it? I mean, isn't it kind of infinite? I think most people's impression is that if you go out into outer space, you just keep it going on forever. But actually, that's not our belief. We believe actually the universe is probably finite. It's big, but it's finite. It started from a big bang, then it's going to be a certain size by now. But we don't think it's like the Truman Show. You're not expecting to suddenly hit a wall. I mean, the ancient Greeks thought there was a kind of sphere around the universe which we were contained in. But we realize that doesn't really make sense anymore. So we're a little bit like in a game of 3-dimensional asteroids. So here we see the 2-dimensional spaceman going round. Doesn't feel like there's any walls or something, but there he is going around the torus. But we're living in a 3-dimensional universe. So maybe our 3-dimensional universe is connected in the following way. Suppose this is our universe. It hasn't got any bigger than this lecture theatre. So we could go out this side, the right-hand side, my right-hand side, and come in the left-hand side. Or we could go out the top here, and where will we reappear? We'll reappear through the floor. And then I've got a third direction. That's like the game of asteroids. I've got my screen here. But there's a third direction. I could go out the back of the stage. And where will I come back? Through the back of the theatre. So we could connect up our universe in that way. It's a finite universe just contained inside this lecture hall. It doesn't have any walls because when you go out that way you come inside here, and this is what your universe will look like, because light is also doing the same thing. It's going out, the light in the back of my head is shooting out there and coming back there. I can see myself at the back of the lecture theatre again and again and again. And so this is a possible model, a possible shape, a possible mapping of our universe using topology. This is a three-dimensional torus or bagel. It's a three-dimensional universe wrapped up in 4 dimensions to make a 4-dimensional bagel. So the real challenge for the mathematicians has been, well, what are the other possible shapes our universe could be? This is one. It might be possible that the star you're seeing out there in outer space is actually our sun, but the light just coming round and reappearing, and we're seeing that sort of cyclical thing. Well, we have actually now reached an amazing conclusion. A Russian mathematician called Grigory Perelman, when offered the challenge of what is the shape of our universe, has now come up with a mathematical possibilities for the shape of our universe. Our three-dimensional universe, if it's wrapped up in 4 dimensions and is finite, using topology, he's able to list now the possible shapes of the universe. This was his solution to the Poincare conjecture. He was offered a $1 million prize, won a Fields Medal, our version of the Nobel Prize. He turned all of those down because for him the glory and the prize was for discovering these possible shapes, these possible maps, topological maps that our universe could be. And I think it is only mathematics that could help us to map the universe. Thank you.